Greetings and welcome, friends. Mr. Waddy here. We were talking about rotations yesterweek. And yeah, here's some homework problems that we're going to take a look at. It says, trace the polygon. Did it. Copy and paste, amigo. And point P, then draw a rotation of the polygon about point P using the given number of degrees. So here's my polygon. I also happen to have a protractor here ready, my digital protractor. Let's see how well I can do this. I don't know. And also, wait a minute, where's my point of rotation? Where's it hiding? Yeah, it's like on the figure itself. So so that's going to be interesting. That point, when rotated, will obviously get mapped onto itself. So let's see if I can set this up. So when I set up my protractor, I line its center up at, oh dear, that was not the one I wanted to do. Huh. I'm going to have to know how to do this in a minute. Wasn't there a way I could... Oh, no, okay. This is the one that I opened. Yeah. So, actually, wait a minute, guys. Did I just see, like... I thought I just saw... Can I move? I want to move that point. If I could line that point up, that would be amazing. Sorry, I'm just like completely not talking about the math right now and just all about my little digital device. So anyways, so yeah, line up your protractor with its center at point P, and the edge along, I don't know, one of those points that are not P, because we can already map P to itself, and I'm going to measure out 130 degrees, and a positive angle is going to be measured counterclockwise, unless they specifically say something else. All right, so so there we go. So let's what we shall do then. Let's see. I'll start with blue. So for Q, if I want to rotate Q 130 degrees, that's going to be. Oh, I don't have 130 over here, guys. So what's supplementary to 130? I think that's 50. 50. So right about there. And I can, oh man, guys, I'm already messing up. I've got to click on a different layer for my writing. Telling you, like, there's so many things I've got to remember to do this little trick. So let's draw with a straight edge. We'll line up one at here, point P, point Padre, the other at 50 degrees, and we'll... And the other one I could line up over here. Is right Q units away, and what I'm going to want to do, right, I know it's going to 130 degrees is that much, but I got to figure out how far would Q units away be, or how far would a segment congruent to PQ land. And the way we do that is with our compass. So your circle tool, which you guys have one that's a little different than mine. But you would line up your rotational point of your compass, like so, and then you change the radius of your compass to be of PQ's measure, and then you'll swipe like that. And the intersection between these two things is going to be Q prime. Q prime. And it's going to be great. It's going to be great. I like it. All right, now I've got to figure out this next point. So I'm going to rotate my protractor again. I think I'll end up needing it somewhere like about this. Because, yeah, I've got to rotate R 130 degrees, right? Once again, still counterclockwise. So here's R 130 degrees. That's going to be at my 50 mark like that. That's unfortunate that these are going to be close to one another. And when I draw my line, it's going to be something like said. And so there's that value. And here is this one. Did I go out far enough on that other edge? I might not have. No, I did. I did. And we'll do the same thing with our compass tool, which is still lined up at center P in my case. And we'll change the radius to be equal to the measure of RP or PR. And swipe, like so, and there we are. So here is going to be R prime, And we already said that P prime is going to land on itself because it happened to be the point of rotation. And so let me draw the end result figure. Nope. Man, Mr. Waddy, come on. What is this? All right. So yeah, it would have been this to this. I feel like, man, that green is not showing up over that blue much at all. And then over to the R prime. Good times, good times. And then over to the P prime again from the R prime. And so here is my new triangle, P prime, Q prime, R prime, something like that. It is going to be congruent to the original because rotations are a rigid transformation. All right. All right, graph the polygon and its image after rotation of the number of degrees, 270 degrees, and this is about the origin. Let me see if I can, I guess this might end up being a little lower resolution than I want. I'm going to pixelate it a little bit. Bam. Look at it, it's good enough. So if I want to do this rotation about the origin, this point is easy, 270 degrees, it would be like whip, whip, whip. And it makes that sound effect. So S prime is 3 units away this way, and then when I rotate it, sorry, S was 3 units away that way, so S prime is going to be 270 counterclockwise, like so. So these ones that happen to land on an axis are pretty easy to measure. R prime is then going to be up at 0, 5, like that. But this one's a little bit different. If I want to map T, I guess I usually try to do these almost like at 90-degree jumps at a time. So if T is at -1, -3, it looks like 90-degree rotation would have landed at this spot at 3, -1. And then another 90, or 180, would have landed at this spot, 1, 3. And then another 90 would have landed over here, at what looks like -3, -1 is T prime. I guess I could also have just thought of that as a backwards 90-degree instead of a 270. So there's T prime, and I'm fine with you guys kind of doing this sort of like mental rotation. But let's do Q using another strategy. So this appears to be -6, -3. And we also learned these properties, these rules for rotation about the origin, where you could actually have some tricks based on your coordinates. So for 270, and I don't need you guys to have these memorized, but they're true, they exist. Yeah, I'm gonna swap the x and the y coordinates, and then opposite the new y coordinates. So in the case of Q, Q prime must end up being at -3, +6. -3 and +6 would be Q prime, because I've swapped the coordinates, and then the opposite of -6 is +6, right? Like so. So yeah, so that's kind of what that would look like. And yeah, I can't draw very straight lines myself. There we go. So there's your new quadrilateral. It appears to be a trapezoid because it has exactly one pair of parallel sides. Not bad, not bad. Yeah, we talked about that. Oh, and then function. Function composition. Come on, it's not the only kind of composition, Mr. Waddy. We're doing transformation compositions here. So let's do this rotation and then reflection. So for X, for a 270-degree rotation, we'll just do the -90 and do the quick jump. So here would be X prime, and then over here, this is at 4, -5. So it's going to be at, what, 5, 4? Over 5 up 4, I think. No, that can't be right. What did I do wrong? This is at 4, -5. Sorry, -5, -4. That's correct. For y prime. Right? And then they asked us to reflect it over the y-axis. And the y-axis is the same as the equation x = 0. It's a vertical line that passes through 0 on on the x-axis. And so if I reflect these, reflections I think are usually a little bit easier. This is 1 unit away, so 1 unit over here, and perpendicular, that's x double prime. This looks like 4 units away, so 4 units away over here is going to be a y double prime. Yeah, and then something like that. I don't know. You guys can imagine lines in your head. Yeah. So there's that. And then we also mentioned the other day that if I reversed the order of these transformations, they most likely will not result in the same final product. Okay, rotational symmetry. Describe any rotations that map the figure onto itself. So for rotational symmetry, usually it's going to be about the center of the object, and then you would pick some reference point. So usually one of the vertices of your polygon would make sense, but I could even pick something like that and then find out when it maps to that same spot each time. And that's fine. That would also work, but why make life harder for ourselves? I'll choose the armpit of the starfish. Yes, I remember that. Good old starfish armpits. And it looks like if I was to rotate here or to here or all the way around here or all the way around there, that would map onto itself. There's 5 types of mapping that could happen. So to find out that angle, I would do 360 divided by 5, which I believe is 72 degrees. So that means increments of 72 or multiples of 72. So 72 would be the first one. 144 would be the next one that would land. Whoop whoop. And looks like what, I don't even know, guys. What's that going to be with the 3? Wow. All right. 200. What? Guys. Why can't I do basic math? It ends in a 6. 216. That sounds good. Yeah, and that's 72 less than 188, which that one I could do. Oh man. Wow. Color me embarrassed. 288. Right there. And if I add 72 to this, I should get 360. But we don't have to write 360 as a possible rotational symmetry. All right, last question I'm going to look at is a let's fight, friends. Yes, my friend claims that rotating a figure by 180 degrees is the same as reflecting the figure in the y-axis and then reflecting it in the x-axis. Is my friend correct? I'm assuming it doesn't say about the origin, but the fact that they mention the x and the y-axes, I'm assuming that's what they mean. So yeah, so if I had some arbitrary point here, and I rotated 180 degrees, let me pick a point that's a little less like that. So 180 degrees would have landed here, right? Is that the same as if I was to, I'll use purple here, mirror it, reflect it over the x-axis, and then over, right, the y-axis, and it looks like it works in that case. Is there a situation in which that wouldn't work? Yeah, if it's on the origin, it would get mapped. A rotation would land it in the same spot, and reflections on both of those would still land it in the same spot. Here's the book's argument, which is one that I'm less inclined to make, but I think it's an interesting argument. They say the following: a reflection in the y-axis and then the x-axis yields xy becoming the opposite of xy, and then the opposite of x, the opposite of y, and a 180-degree rotation also results in the opposite of x, opposite of y. So that's like a pretty solid argument, but yeah, so that works out. So a composition of reflections over the x and y axes is the same as a 180-degree rotation. All right, thanks for watching, internet friends. Bye-bye.